This is the second part of the talk titled Rank 1 Phenomena in Convex Projective Geometry. The plan here is to sketch proofs of theorems 1 and 2 from part 1 of the talk. I'm going to assume that the viewer has already seen part 1 of the talk. Here omega denotes a properly convex domain. Let us recall the statements of theorems 1 and 2. Theorem 1 states that an automorphism gamma in the automorphism group of omega is a rank 1 automorphism if and only if gamma is a contracting element. Theorem 2 states that if gamma is a discrete subgroup of the automorphism group of omega and gamma is a rank 1 group, that is, gamma contains a rank 1 automorphism, then either gamma is virtually cyclic or gamma is an acylindrically hyperbolic group. Theorem 2 follows from the forward implication of Theorem 1. Here is a sketch of that proof. Since gamma is a rank 1 group, by definition, it contains an element gamma, which is a rank 1 automorphism. The forward implication of Theorem 1 implies that gamma is a contracting element. Then it follows from results due to Sisto and Osin in the theory of acylindrically hyperbolic groups that either gamma is virtually cyclic or gamma is an acylindrically hyperbolic group. This finishes the proof of Theorem 2. Now we are going to sketch the proof of the forward implication in Theorem 1. Before doing that, let us recall the notion of rank 1 automorphism and contracting elements briefly. An element gamma in the automorphism group of omega is a rank 1 automorphism provided it satisfies the conditions on the left. That is, lambda 1 bigger than lambda d, while lambda 1 and lambda d are the maximum and minimum modulus of the eigenvalues of gamma tilde, where gamma tilde is a lift of gamma. The second condition is that omega contains an axis of gamma. The third condition is that none of these axes of gamma are contained in a half triangle. If an element gamma in the automorphism group of omega satisfies the conditions on the right, we say that it is a contracting element. The conditions are, number 1, gamma needs to be an infinite order element. Number 2, if we fix a point P in omega, then the image of the group generated by gamma under the orbit map should be a quasi-geodesic. And the third condition is that there exists a coarse projection pi AP that maps omega onto the quasi-geodesic AP. And this projection map needs to have nice contraction properties. The goal here is to show that a rank 1 automorphism is a contracting element. In order to prove that, the conditions that we have to verify, some of them are relatively easy. So we are going to concentrate on the interesting part of the proof. This is what this remark says. So the remark says that in order to prove that a rank 1 isometric gamma is a contracting element, it is enough to show that if L is the axis of gamma and pi L is the closest point projection onto the rank 1 axis L, then the projection has a certain property. The property is that there exists a positive constant C such that if x and y are points in gamma for which the distance between their projections under pi L are at least a distance C apart, then the projective geodesic between x and y passes through the ball of radius C around pi Lx and also passes through the ball of radius C around pi Ly. I will now try to sketch the proof of this remark. For the rest of this proof, we will assume that L always denotes the axis of the rank 1 automorphism gamma. We also set up this notation that delta ABC will always denote the projective geodesic triangle whose vertices are the points A, B, and C in omega. First, we have this lemma. There exists a positive constant D so that if P and Q are points on the rank 1 axis L and X is in omega, then the projective geodesic triangle determined by P, Q, and X is D thin. In order to prove this lemma, we will use this fact that was proven in a joint work by Andrew Zimmer with myself. And this fact says that in order to prove lemma 1, it suffices to show that there exists a positive constant d prime so that the projective segment between P and Q is contained in the d prime neighborhood of the union of the projective geodesic segment between Px and Xq. I will now try to sketch the proof of the statement in this box with the black boundary. Suppose this is false, then for all natural numbers n, I can find points Pn, Qn, and Xn which satisfy the configuration in this figure. That is to say that there is a point Zn in the projective geodesic segment between Pn and Qn, so that if we construct a ball of radius n around Zn, then this ball does not intersect the segment Pn Xn, and it also doesn't intersect the segment Xn Qn. Since gamma acts by a translation along L, we can translate Zn using different powers of gamma and assume that Zn converges to a point Z in the interior of omega intersection L. Translating the entire picture by the same powers of gamma and passing to a subsequence, we can assume that Pn converges to P, Qn converges to Q, and Xn converges to X. Since all these sequences were in the projective space, we can pass to a subsequence and take limits. Now we will try to understand what happens to the configuration of the 4 points Z, P, Q, and X. Because of the way the points were constructed, this is what happens. The point Z is in the interior of L, but the projective geodesic segment Px, which is now in the boundary of omega, the segment Qx is also in the boundary of omega. So we end up seeing that the rank 1 axis L is now contained in a half triangle determined by the points P, X, and Q. Now this is clearly a contradiction because by definition, a half triangle cannot contain a rank 1 axis. This concludes the proof of lemma 1. Now we will prove a second lemma towards the proof of the remark. Lemma 2 says that there exists a positive constant C prime such that if X is a point in omega and Z is a point on the rank 1 axis, then there exists a point P in the geodesic segment XZ such that the Hilbert distance between P and the projection of X on L is at a distance at most C prime from each other. So what this lemma is trying to say is that if X is any point in omega and Z is any other point on the rank 1 axis L, then the projective geodesic segment joining them passes through a ball of radius C prime around pi Lx. Proof of lemma 2 follows from two different things. First, it's lemma 1. X is a point in omega, pi Lx and Z are points on the rank 1 axis. So if we take the triangle with vertices X, pi Lx, and Z, then this triangle is D thin by lemma 1. The second ingredient in the proof of lemma 2 is the fact that pi Lx is the closest point projection of X on L. Hence, the distance between X and Z is going to be greater or equal to the distance between X and pi Lx. Using these two things, we can prove lemma 2. I'm not going to go into the details of the proof of lemma 2. I will try to use lemma 1 and lemma 2 now to prove the remark. We will prove the remark by contradiction. Let us suppose that the closest point projection pi onto the rank 1 axis does not satisfy the conditions that were laid out in the remark. If that is the case, then for every natural number n, there exists points xn and yn such that we will have this configuration. What this configuration says is that the projective geodesic segment between xn and yn never intersects the ball of radius n around pi l xn, and pi l yn is at least at a distance of n from pi l xn. Again, since gamma acts by translation along the axis L, we can translate pi l xn using different powers of gamma and assume that pi l xn converges to alpha. In fact, translating this entire picture using those powers of gamma and passing to a subsequence, we can assume that pi l yn converges to beta, xn converges to x, and yn converges to y. And now we will analyze the configuration of the points alpha, beta, x, and y. And this is what that configuration looks like. Because of the way the points were constructed here, the line segment joining x and y is in the boundary of omega. The point beta is in the boundary of omega. But alpha is in the interior, so the line segment joining alpha and x is in the interior of omega. What we don't know yet is what happens to the line segment joining y and beta. We will figure that out using lemma 2. That is what we do now. Lemma 2 tells us that we have this specific configuration. Namely, if we look at yn and join it to pi l xn using a projective geodesic segment, then this geodesic segment contains a point Pn whose distance from pi l yn is at most c prime. Now, using properties of the Hilbert metric, we can show that this implies that the line segment joining y and beta is also in the boundary of omega. So we have shown that the line segment y beta, shown in green in this picture, is also in the boundary of omega. However, that leads to a problem because L is a rank 1 axis. And now if you recall the properties of the rank 1 axis that we had set up in proposition 1, then one of the conditions prevented this from happening. Namely, if L is a rank 1 axis, we cannot have a line in the boundary of omega that starts at an endpoint of a rank 1 axis. So the line segment joining y and beta in the boundary must be degenerate. Hence, this forces y to be equal to beta. So in this picture, y and beta collapse. Hence, we end up getting this picture now. But again, we are seeing a line segment joining beta and x in the boundary of omega. Because of the same reasoning as above, this line segment also must collapse because L is a rank 1 axis. Hence, we have x must be equal to beta. Now we are going to apply lemma 2 again. Now we look at the triangle given by xn, pi l xn, and pi l yn. The projective geodesic segment joining xn and pi l yn contains a point qn whose distance from pi l xn is at most c prime. So the line segment joining xn and pi l yn always passes through a compact neighborhood around the point alpha, where alpha is the limit of the sequence pi l xn. Now notice that xn converges to x, which is equal to beta, and pi l yn also converges to beta. So the line segment joining xn and pi l yn must also run off to infinity because both of its endpoints are going off to the same point beta in the boundary of omega. But then lemma 2 says that this line segment must always intersect a compact neighborhood around the point alpha in omega. Hence, x cannot be equal to beta, and this brings us to a contradiction. So we have proven the remark by means of contradiction, and hence we complete the proof of the forward implication in theorem 1. The proof of the converse implication in theorem 1 uses properties of contracting elements and the dynamics of automorphism gamma on the projective space. Since I have not spent a lot of time talking about properties of contracting elements, I skip the proof of the converse direction. And this is the end of the second part of the talk. Thank you for your patience, and thank you for listening to me.